And I would like to solve this problem for those of you who have not, there will be some of you who have not seen this problem, and those of you who have seen it from the afternoon session, I'm gonna solve it from the beginning. So, because there was at the end from the other session a question, and I need to go clearly, and I think I want to make sure that it's recorded. All right. Okay, so this one, it shows the problem here shows two current filaments and they are semi-infinite. So for example, the one that is along the z-axis starts at the origin of the coordinate system. Let's assume that this point here is O, and it goes from infinity, goes from O to infinity, but the direction of the current is like going from infinity to 0 to O, and then the other, then it continues on Y, on the y-axis from the beginning of the coordinate system, and then it keeps going up until infinity. And the problem is asking you to find the solution to this for two separate points, but let's start with one point and then we'll do the other one. Okay, if you wanna ask me anything, just speak out because I cannot watch the chats, the chat activity. Okay, what I said is in the book, and I want to tell you what page on the book, in the book, we had the solution of this problem, the one that we see. And I think it was, let me find it 1 second. One. Yeah. Okay, it's page 301 from the book. If you go there, this is the problem the book solves. And as a matter of fact, instead of A, instead of row that the book has, instead of H that I have here, the book has row. But other than this, it's the exactly the same expression here. And the magnetic field at point P, rather not H, but P, is given by this expression. So along the phi direction, which means that if I were to write a circle that that would go like this, not that one. Let me do this. Okay. So rather the magnetic field, it's if this is a cylindrical coordinate system and that's the center of this, then the magnetic field at that point goes along the phi direction. That's what it means. That's the phi direction. And this one is here, H. All right, and that's the current times 4 pi H. And then there are these two angles that you see are very important. All right, so now this is what we have from the book, what we have seen. And now we want to apply this formula to these two currents. So here is what I do. Let's look at the current, which is along the z direction. So this is going to be, we call that I1. And we call this I2. And they are semi-infinite. So let's take I1. I1 for us goes from infinity comes down to 0 or to O, if you like. Let me do this like this. okay? So it stops at this point and has this direction. And this is point for us, it would be point O. All right, point O is here. Why is that? Okay, O. All right, now we're gonna find the field at point P. So let me in fact move O here. And point P is, if this is the Z direction, what did I do? If this is the Z direction here, this point is along the X direction at P. All right, let's look at this one, what we have here, at the one that we have out there. There are two ways of doing this, but let's assume that I would like to keep the orientation of the current, all right? So in other words, think of my point B being my point O, and think that point A goes to infinity. So practically, if I were to flip it over, okay, I would have here, up here. Let me take this, so for a moment, let me take this one down here. And let's think of this case where I have a current that stops at B, but it comes from infinity. All right, and then stops at B here, comes from infinity, comes like that. And then my point P is somewhere here. I think that will be more similar to what I have, all right? That will be similar to what I have here. So if I were to consider that the arrangement, then let's now find the angles, A1 and A2. So if P moves up there, then this is A2. All right, and if A goes to infinity from here, if A moves to infinity, then practically to find A1, I would have to extend that down to infinity, which practically would make A1 to be 0. All right? It's like the same as I bring the point P along the same line with A. So that would make A1 to go to 0. All right, in that case, if I have this arrangement, I make it a little thicker. If I have this arrangement, that at point P, since the current goes up, all right, it goes, if you use your right-hand rule, then the circle of the H sub phi in this case would be this one. Let me make it thinner, and also this one. So this is where H sub phi is gonna go, and in this particular case, the H sub phi will go like this. Why? All right. That would be H sub phi. All right, and H sub phi in this case would be equal, rather, so I can see it, I over 4 pi h, and cosine A2 will be 90 degrees, so it's going to be 0. I would write it cosine 90 minus cosine 0, and therefore this would be I over 4 pi h minus 1. All right, so if is to go along this direction here that I have, the negative sign will make it going along the opposite direction. All right, so in reality with a negative sign there, if I put there h, it would be minus 1 I of 4 pi h a sub phi, which practically it will force it to go along the opposite direction here. All right, so let's keep that in mind. Now here, the situation as if my B is O, all right? My P is my P here, and the this, so, and you think that here phi, it will be perpendicular to the distance here, so it's along the phi direction. So obviously for the Cartesian system, being perpendicular to this, and this goes like that. That would be, let me see, according to that, it will be along this direction. No. Let me see. It would be, if this was Z, and if this, they would come toward, this is X and Y.
Dr. Kataki.
Yes.
So I was looking back at your like solution.
Yes.
Can you explain why it's cosine of 0 as opposed to cosine of 180? Because like looking at the diagram that you drew above it, if it's extending all the way up to infinity, or if I'm sorry, if the point A is going all the way to infinity, then A1 would be. Do you mind if I annotate on your screen?
Yeah, you can, let me see.
I'm not. I'm trying to find the annotate.
Wait, I think you can, okay, yes, annotate.
I'm trying to find the option, but it's not letting me. But essentially, what I'm like trying to say is
Because it
yeah,
goes
it would
on
be
the other.
yeah, and
Okay.
yeah, because I think the magnetic field is in the exact opposite direction because like right hand rule would tell us it's going into the page at P, right? So I'm thinking A1 is not 0, it's 180.
It's 180.
And 180 would give you minus -1, so it would be +1.
Okay. The way, in fact, to see that even, it's the direction of the field. So practically, if the field goes, I mean, it can come out of this sign, or you can go with the direction of the field, because with the right hand rule. So with the right hand rule, practically it needs to go like that. Yes, but I understand what you're saying, and you're correct in this particular case, because it's the outside. Yeah. Let me see. But if I were to do that, the direction, if it goes down, so the direction for this would be the opposite of that one. So it would be like this. Right? It has to be like
Yeah,
that.
yeah, that looks correct. So
I
I'm thinking, oh, I'm sorry.
Yes. No, I was thinking that the best way to do that is to take the right hand rule to find the correct direction. And if it is 180 or 0, then, just ignore the sign there.
Yeah.
Yeah, that's the best way to do it. It can be confusing. Correct.
All
Yes.
right, thank you so much.
You're welcome. So in this case, right, you can assume that this is 180, which is going to give -1, but I suggest that you take the direction of the, and then you find it from the direction of the current and the right-hand rule. Okay, so you find this one. This, because it's vertical in the Cartesian coordinate system, because that's where we are here, that implies that it's going to be along the negative y direction down here. So this h is going to be h here, let's say from 1, because that is current 1, will be equal to minus, and this is minus ay minus 1, and then I over 4 pi h. All right, so that is what you get from that. From the other one, which is I2, let me also make that here, so we can fit both of these on the same page. Okay, from the other one, then what I do is the following. I consider these two, I2 to be like this. This is I2. Then here it's my point A. B goes to infinity. Then I am at point B. And then, so in this case, this goes to 0. You're absolutely correct. So this one will go, A2 then will go to 0. The other went to 180 because it was external. You're right. And this, no, A2 goes to 0. And let me just use this one so we don't mix it up. 1 second. Okay, so that is this one. Okay, and this one now is 90. Okay, 90.
Okay, so like the left side, assuming that the current is going to the right, is always going to be the outside angle, and then the
Yes,
right end is going to be the inside angle.
yes,
Okay.
yeah. So the one which is behind the current is gonna be the outside. The one which is in front of the current is gonna be the inside from here. One which is behind the current. So if you assume the current goes from A to B, is A1 and is outside. The one which is in front of the current is A2, is inside. Remember that as a convention. But the other thing, as I said before, also to make sure that you have the right signs, check your direction with the direction of the current. So if with the right hand rule, that's what I'm suggesting. Okay, in this particular case, so what happens here is that at point P, H2 will be now, since the current, if you use the right hand rule, and if I were to find a loop for this one, the loop will be like this, and the phi direction for H, for that direction of the current, would be this one. Okay, so if this is the y direction, and this is on the this one would then go is a z direction like that. This one is gonna go along the negative, let me see, along the negative z direction. Am I right? So because it's gonna be, yeah, and I'm not correct in how I have done this, but it's gonna be like this. It's gonna be parallel to the loop, and that loop is gonna be on the XZ plane. It's gonna be parallel to that. It's gonna be perpendicular to the X direction. Therefore, it's gonna be along the negative Z direction. Okay, so it's gonna be minus AZ, the direction there, and then it's gonna be I 4 pi 8, and let me see the angles there, just make sure. The first one, A1 here is 90. So the first one is Z is, yeah, it's 90. So it's 0. The second one is like 0. Cosine A1 is gonna be 0 up here. So cosine A2 is 0, that gives 1, so that is correct here. So practically we have this one for H2 and this one for H1. And if we were to get rid of this for a moment, then what we would have is at point P, we would have two components for H. Okay. So if this is Z, just 1 second, let me finish this problem. Z, X, and X and Y, and we are at this point P. So 1, and I said B, and that was supposed to be, what B did I put there? Z, okay. I'm sorry, I cannot even read my own thing. Z, okay. So 1 would be along the negative Z, one component. The other is gonna be along the negative Y, this component. So you remember this one goes like that. And therefore, the two will give me 1 second here because it's gonna go on the other line. All right. So the two components, they're identical. And if for a moment were to erase this, just for a moment, I will put it. So the two components there would be like that and are identical. So this is going to be 45 degrees. And if I were to write X like this, so X could be like that. So it does X is like here. So that is Z minus Z, that's minus Y. And that's how it goes at this point.
What did you use to determine the directions again?
Okay. So this one, for this one, so for this current, we use the right-hand rule. All right. So if you look at the first current that goes down, just compare. This one is I1 and this one is I2. This one here is due to I1. And this one here is due to I2. All right. And I1 goes down, so it turns around. So this one is parallel to a loop that looks like this. All right. And this one, so it looks like that, the loop goes, but because it's down, it goes to the negative Y. And the other one, if I want to erase this because that becomes too complex, the other one, which is down here, okay, so take the right,
5 o'clock.
Take the right hand rule, it would have to be on a loop like this and down. So this loop, it is on the XZ plane. The other loop was on the XY plane.
I mean, if it's on a loop, couldn't it be on like two different directions? Because
Yeah, there are two different directions here. And then you take you find the sum of the two. So one is along the minus AY direction, and the other is along the minus AZ direction.
I mean, for like a single current going through like the magnetic loop on it, since it's just a loop, wouldn't it?
It's not going to be one, yeah, but the loops will deform, all right, because the current is taking a turn at this point. I mean, for an infinite current, the loops remain the same, all right? If you have an infinite current, the loops will look like this. If you have a current like, if the current was in that direction, then the loops would turn. Say this goes like that, and the loops would go like, let me see, like this. Now, if your current was to turn here, I will use the difference. So the current will go like that, and will go like this. Then the loops for this one will turn like this. And will go like that. But when the current comes here in the corner, then the loop here is going to deform. Approximately, I would say the loop here is going to look more like this. And that's what you see here in the corner at this point. So the loop here would go, see what I'm saying? Can you visualize that a little bit?
Okay, so it doesn't form at the or wait, it's trying to accommodate the like movements of both fields. Is that what it's doing?
Yes. So it accommodates the fact that you have at this point, you have two currents that contribute, this current and this current. So there is a magnetic field from this, and there is a magnetic field from this. And that's why it turns like that, the loop.
Okay.
So like take a little bit of time just to visualize it, you know. I mean, the loop has to turn from this way, the purple loops are, they have to turn eventually to look like the pink ones. So at the corner, it's going to be like that. And think that the corner, this is the Z direction, this is the Y direction. So as it comes to the corner, and then you look, your X direction here is like coming perpendicularly down to the plane that you have in front of you. Now think that along that direction, the field is gonna say, if this is, for example, so your X direction there, if I can do this to help you, your X direction there is gonna come and it's gonna look, it's gonna come out of the board and it's gonna be looking towards you. And right there, the field, you see it, you could almost see it here, that blue loop, I will do it with green here. It's gonna look like that. And this line that you see here, even if I cannot do it very well, obviously, but it's perpendicular. So right, it's gonna be right here. Let me see. I cannot draw it well. Let me just tell you. So let me do the blue. So if this is the loop here, all right, then it would go like this down. How would it go? Um, mm, so it would go like this down here, and assume that you are up from this side. So you assume that you are looking this from that side somewhere. I mean, it's I cannot just do it better than that. I mean, by hand, but somehow the field that you found, the, the field that you found there, this field here, is nothing different than this one. They're all parallel to a loop, and this loop, to be better, if I were to do it a little better, will be much more thin. Like I would make it like almost like this. So it when we see it, the way we see it, like here is almost, yeah, you know, your point P is right there, and that's what you see. The bottom line is in all of this to trust. So don't get too much confused about the angles, but trust that the direction of the current is going to be determined by the right-hand rule. So if you look only at one current, like this one, if you look only at this current, so the direction of that field is going to be determined by the right-hand rule. If you look on, even if it's finite, if you look, for example, only at this one, then the direction is going to also be determined by the right-hand rule, even if it's finite. And then, so that's why you have the two components here, which are along different directions. And those directions are better determined by the right-hand rule along the two for H1, and for H2. The other thing, I mean, if that is more difficult to consider, is to, somebody can give you these two sections separately without necessarily being connected, and say, I have one section of a finite current in one location and another section of a finite current, and ask you to find the fields in between. So even in that case, so the one thing you need to remember, it does not matter if your current is infinite, as long as it is a current that flows along a straight line, then it's the right-hand rule that is going to help you identify the correct direction of the magnetic field that is created by it. Keep that in mind. And use that, because it's better to do this through the right-hand rule and find the direction of the magnetic field instead of trying to do it through mathematics, because it's going to be trickier. So again, as I said before you even start writing mathematics, trying to find the direction of the magnetic field that you have from the right-hand rule. And then you go to find the value. And that will be the way to solve the problem. So what I will do is that go to the other room that I have to go, and I will connect from there. So don't leave. I will be back in like a few minutes. Okay? Can you hear me?
Yes.
Yes.
Okay, thank you. Just 1 second. Okay, can you hear me now?
Yes.
Okay, perfect. All right. Um, do we have any questions, any additional questions on this problem before I leave that one? All right, so.
What was the total electric field at this point?
Pardon me?
What was going to be the electric field at this point at P?
The
Which,
magnetic field, you mean?
yeah.
Yeah. So it will be if you take the two fields and then, so let me, just 1 second. A moment, let me find my pen. Let me find my pen, 1 moment, and I'll tell you. Ah, there it is, on the right. Okay. So A sub y, so if you take is practically, let me see, this one. These two, so the total field H would be minus AY minus AZ of I 4 pi H. That is the field in Cartesian coordinates.
Thank you.
You're welcome. All right, so another one different from this, not very different in terms of the formula you're going to use, but different as outcome. So here you have a loop, but the loop is this triangle. And let's assume that we have formed it in a way that the three sides are identical. All right, so it's equilateral, yeah. So you have a triangle that is from here, this side. Say this side is for example, centimeters. So there will be, if this is point A and point B and C, then A, B equals B, C equals CA equals 4 centimeters. And the current flows like this, has this kind of a flow, rather, and it's 5 amps. And we want to find the field at the center of the equilateral triangle. So let's remember a few things about equilateral triangles before we do anything else. So in an equilateral, what we know is that all of the angles are 60. We know that the center, let me do it a little better. Sorry, because you might have a lot of, so straight line here. Okay. And then when you write this, let me see, when you write this line, Okay, that will go at the center from, sorry, this is A, we said, why does it write like that? Okay, because, okay, that will be A, B, and C. So this is going to be the center of AB. And then it's not going to be exactly correct now the way I'm doing it, but so if this is, let me erase this for a moment before we go there. So if this is 60, then this is 30. All right, so we remember that because this is, if AB is 4 centimeters, then AO will be 2 centimeters. All right, and if AO is 2 centimeters and AC is 4 centimeters, then you know that CO also, CO from there will be the square root of 4 minus square root of 2, which is 16 minus 4 square root of 12 in centimeters. That's going to be CO. Okay, the center now of this, you will have to write the line that goes from here, there, and that is expected to be also perpendicular. This one here, this is 90 degrees. This is 90. And then this other line from here is going to be 90. So that's what we know. And that's the center. We solved the problem with equilateral triangles, all right? So where that is O, and that the center, we called it O in this case, so that has to be something different. So, oops. Call that, say, O prime. Okay. All right, here, O prime. And that's O. So what we want to find is the magnetic field at position O. We know now that this is 30 degrees here, this angle. We know this is 30. And we also know that this will be 30, all right, which implies that this one is going to be 180 minus 30. Why? This, okay, this is way too big. I wanted to do this one. Make it 180 minus 30 is 150. So practically, okay, today we have problems with this. There, delete. Okay, so this one is 150. I'll remove the 60 from here for a moment because we don't need that 60. All right, so this is 30, 150, 30 the other one. Now, what we really need to find, where am I going to? If I know that the current here flows like this and like this, then what I really need to find here is the magnetic field from only one of these sides. Let's assume that I take the side AC. What am I looking at? AC. Then if I take this, write this here, this is A, C, this is at the center, I extend it by a distance. We have to find this distance. This is going to be O, all right? And then connect this here. This is going to be 30. And then connect this one here. And if I extend that, this is going to be 150. And the current here goes like that. So if I go back to this formula here, all right, so I can take this one here, copy it, and I can go down here, paste it. And now, A2, let me see. I need to remember what A2 is. A2 is up there, the internal, A1 is the external line. So A2 is this one. That's A2. And this one here is A1. And the distance, H, so H is O double prime. All right? So how I find O double prime? From here, from the equilateral triangle. So what do I know? I know that OC or OA, if you like, but let me call that OC, call a double prime. I know that this is a orthogonal triangle. I know that one angle is 30 degrees there, so this is 60. All right. I know that OC, I found it, is square root of 12, whatever that is, square root of 12. Let me see, find that. 12 square root is 3.46. So this CO is 3.46 centimeters, while the other O double prime C is 2 centimeters. So if we come here and we have CO, we said CO is 3.46, then we know that O double prime C is 2 centimeters. Then we find that O double prime is the square root of 3.46, which is like 12. Square root of that square, which is 12. 12 minus O double O double prime C to the second power, which is 4. 4. So that is going to be square root of 8. And square root of 8. Square root, that gives 2.82. 2.82 centimeters. So now I have cosine, so now I can write this, okay? So this is 2.82 centimeters. So if I add one more page, what I have here is that H from this AC, all right? So from the AC side is gonna be 8 sub 5, I will come to this. Let me wait for a second, put 8 sub 5 here, and we will determine what this one is. And then I, which is given, divided by 4.8, which is, we know, cosine A2 is cosine of 30. How much is cosine 30? Minus cosine of 150. Okay, let's figure out how much, what is the direction in this case of A phi. If you follow the right-hand rule, then this is going to give you, since the current follows the direction from A to C, then E phi is going to be the direction which is perpendicular to the plane of the triangle and going inside the plane. So at that moment, at that point, the direction of the magnetic field is going to be like that. So A phi is going to be perpendicular to the plane of A, B, C, and it's going to go inside the plane. All right? And because you have the same direction in all of the currents will produce the same direction of the magnetic field and the same magnitude. So at the end, the total field in that position at O is going to be the superposition of the three fields which have exactly the same direction and the same magnitude. So it's going to be that H total is going to be along that phi direction, which is perpendicular to the plane A, B, C, and going in the plane. And it's going to be 3 times the current, which we know, divided by 4 pi h. And then it's going to be that. So the cosine of 30, is it not? How much is it? Cosine. So it's point 866. Cosine of 150 is, so it's minus plus 0.866. So twice that. So this is going to be A phi. So this is going to be 3 times, how much is the current? Current is 5 amps, 5. So I put here amps. Then I have times 0.866 times 2, 2 pi, and h, we found it to be 282 centimeters. So this and this goes and remains another 2. And then we have A phi is going to be 15 times 0.86, so 15 times 0.866, 12.99, say about 13, divided by pi times 2.82 amperes per centimeter. And that's your magnetic field there. That's how you solve this one. Any questions about this?
Professor, I had a quick question.
Yes.
So for the value of CO, you use 3.46 centimeters
CO.
in the initial picture right there.
Yes.
Doesn't that CO refer to the distance from the top of the triangle to O prime? Because you used 4 squared, which is the, or am I mistaken?
No, you are right. As a matter of fact, that I used CO prime to be this one, and I had CO down there. That's what I did. I changed the prime and without changing that. So that's going to change the value, obviously. So this is CO prime. Yes. So then, but then the difference, how do I get? Oh, there is another way of getting, obviously.
Yes, I used 2
Yeah.
times tangent of 30 to
Yeah,
get
exactly.
1.155.
Okay, perfect. Let me get that. I will write it here. Yeah, see, I change whenever. That's the one lesson. Never change the sign. You never change the symbols without going back to correct. So the you find, so O double prime, then it becomes O double prime C, and then becomes the divided. So the tangent is going to be O double prime Okay, let me write it this one. Yes, you did it correctly, but I need to write it here. So this divided by O double prime C is tangent of 30. Okay, and then since we know that O double prime C is half of that, which is 2 centimeters. How much did you find that then?
1.155 centimeters.
1.5. Okay. In that case, then that is 1.5, 1.55. Okay, and okay, yes, thank you. The other problem that somebody could give is the following. I have another problem here, and then we'll go to electrostatics. This problem here, this says too infinite long. I will not show, I will not talk about force here, but since we have not done examples with forces, but I will modify the problem for a second. So show the two infinite long parallel straight filamentary conductors along the z direction with a separation distance d at currents I1 and I2 in opposite directions. How I would modify this problem is to say, what I could give you is to say, prove that the maximum field is in between the two conductors. Or I could ask you to find the field if this is in the center here. Say find the field or find the field along this line. Since they are infinite, okay, so it will be the same everywhere on this line. Or I could just say find the field at the point O. So that is exactly superposition. You take one current, and then, so you take I1, goes like this, and it has a magnetic field that goes, let me see, magnetic field here, goes like that. The other one goes in the opposite direction, goes like this. So the magnetic field from there would go like this. So the two magnetic fields superimpose. And in that case, you will have to just find the field here, which is, if this is the way here they have it is, this is the y direction, this is the x direction, and this is the z. The field here is going to be along the positive x direction, the total field. And so H here is going to be along the x direction. I'm not supposed to do that. Okay, let's take this one here. Along the x direction. And how much is the field from one infinite long wire? Is I divided by 2 pi or 2i. Let me see, I think it's 2. And the distance, 1 second. So that, I want to make a mistake. It's from the book infinite long wire. You mean line can 1 to pi? Okay, it's good. 1 to pi and the distance. So if the distance between the two wires, say this one was to be d, then, or 2d, then here it would be d. So it would be times 2 because of the combination of the two currents. If I1 equals I2. If they're not equal, then let's assume if here there are two. If they are not the same, in this case, it's going to be so that is a simple problem you can do. Do you have any other questions in magnetostatics before we go back to electrostatics?
Hold on. So this is just the what you used here is just the equation for a infinite.
Yes, infinite light current, which is at page 310 of the book.
Okay.
Yeah.
So just checking.
Yes, book. Page 310. I could give you some problem like this with the charges, but with 3-point charges. So for example, another problem. Let's assume that you have an equilateral triangle, but you have 3-point charges, like this. And you would like to find the field at the center. So practically you will have this one here, and this one, and this one there. And you would like to find the field here. Now this is electric field, okay? So this is Q. Let's assume Q and Q. So how is it gonna look here? No, on the basis of what we know, this is gonna look like that, the direction of the electric field, all right, at this point, assuming it's all positive charges. And the other direction would look like this. And the third direction is gonna look like this. All right, so, and then what's gonna happen at the center? How much is gonna be the total field at the center? What do you think?
It'll cancel out.
Yes, it's gonna cancel, exactly, it's gonna cancel out. Why?
I think it's symmetry, and also just I remember that was one of the homework problems.
Yes. Because of symmetry, what exactly symmetry? Here, so let me do it. Here, if I just take only this piece, all right, and I write it here, down here, this is gonna be the direction of one component that comes from the upper charge. Then at 160 degrees from here, or not 160, what did I say? It's 360 divided 120 degrees from there will be a similar in magnitude. This is going to be 120. And then from 120, also the same, 120 here. Those three will cancel out. Why is that? If I take two equal vectors and I place them in the 120 angles in between them, what they're going to give me is two isosceles triangles. So the sum of vector A, say if you call that A, vector A, the sum of this vector A of this vector B, which is this vector C, then vector C is going to be equals with A, will be equal with A and equal with B. And this angle is going to be 60 here and this 60 there. But I took now this one and I took this one. So if I have, and the sum of the two became this one. If I have another vector on the other side, which is equal with A and B, and creates 120 here and 120 there, so this one is going to cancel out with this one. And that's why it gives 0. Okay? So that's why you have 0 there. However, if you change the Q in any other way, then it's not going to be 0 anymore. If, say, the Q's are not the same, but one is just one of them is negative, instead of being positive, then the direction change. Because what happens? Instead, this one is going to go like this. All right? To go towards that minus Q. And when it goes like that, you're going to have not these vectors, but you're going to have these two vectors. You're going to have, I'm going to do this. 1, 2, those will be at 120. And then it's going to be another vector here equal to these other two at 60. So practically, what is the sum of these three vectors? All of them are equal. So let's assume this is vector A, B, and this is C. I claim that the sum of all three will be a vector double C along the C direction. That's gonna be, it's gonna be if you have a negative Q there. For negative Q here.
So it wouldn't cancel out if they were all negative?
Yes. If they were
Right.
all negative, it will cancel out.
Oh, sorry, just the one on the bottom right.
Yeah, it's only one.
Okay.
In this case. Yeah.
Professor, so for the negative Q charge, why does C double?
Because you have the following. If you have two vectors that are the same, and there are at 120, so, and if you find the sum of these vectors is going to be a vector equal to those two, as I explained here. So the sum of two vectors that are equal and at a distance of 120, the sum of these vectors is a vector equal to these two and directly at the 60 in the middle. So this, each one of these is 60. All right. Now, if on top of this you have a third vector, you overlay with this one a third vector that is the same direction with the first one, the purple, and is the same value, then the sum of two vectors like this, I'll separate them so you can see them. The sum of these two vectors, one plus the other, will give 2, that vector. See?
Oh, okay. Thank you.
You're welcome. So let me look at another problem. You need to remember How would you do? Do you remember how to solve this problem? It was in the homework. You remember how to find the capacitance for a coaxial? Let me do it well. Let me draw a line here. Let's write it. Let's write the problem. Okay, consider the following coaxial. I'm going to solve so many problems, I will not have anyone to give you. No, I'm just teasing you. Consider the following coaxial. So it's here. And then here. All right. Now, let's assume that we don't have a problem with the outside grounding. All right, so assume that we have taken care of the grounding, so we don't have any problems outside. That does not happen. Okay, so we have these two conductors that make a coaxial line. And you know how to find if I give you, for example, this 2A, and if I give you this 2B, how are you going to find, do you know how to find the capacitance of this?
I think you used the equation on page 253, right? It's the
Yes. So you go to the book, Electrostatics, and is in chapter 6, coaxial capacitor. And they have that C, so book, page 253, you're correct. It gives you that this is equal to 2 pi epsilon L, if there is a length, natural logarithm of B over A. Now, when I ask, this is the total capacitance, all right? When I ask you capacitance per unit length, so this is total capacitance, and assuming that there is a length, that this one has a length, all right? And assuming that this length is L. So this is total capacitance. So I'm trying to see whether it's recording. I'm sorry for. Then if I do not know the length, and I find C divided by L, this is called capacitance per unit length. Okay. So if I ask, for example, for total capacitance, I will have to give you all of these dimensions. But if I ask for capacitance per unit length, that means that you don't need to know L. All right, so you find it from that. What would happen if that was filled with a material, all of it? What would be the difference from what you would do before? In the first case, you would use as epsilon what?
Sorry, what was the question? Or what are you changing?
If that did not have, what would be the difference between the capacitance of this coaxial, but between one case where it had free space, dielectric, free space, and the other where it had a dielectric? Like
the constant, sorry, the constant would change, right, with the
Only epsilon will change, exactly. And how much is epsilon in terms of epsilon naught?
Well, I know that it's like fraction, right? I know that the epsilon naught is it's like 8.85 to the
Yes.
10 to the
And
negative.
epsilon, you need to remember that epsilon is epsilon sub r times epsilon naught, where for air, epsilon sub r equals 1, and for any dielectric material, epsilon sub r is larger than 1. Okay? So practically, the capacitance will change if it's not air, but is a dielectric, it's going to change because epsilon here is going to have an epsilon sub r, which is different than 1. Okay? Is that clear?
Yeah, that makes sense.
Okay. What would happen if now, instead of, let me copy it down. Okay. So now I'm copying this. Copy. Coming here. Paste. So I'm solving a different problem B. And now I remove all of this material and I am only covering part of it with a material. So let me see how I'm gonna do this here. Okay, and let's assume now that my material is here. How would you solve this problem without solving again for any equations or anything? What would you do for that?
So so we're solving for like capacitance again.
Was that? That is an epsilon. Let me tell you. I did not hear your question clearly.
So we're solving for the capacitance
Yes,
again.
exactly. Yes. So where now this one is epsilon, epsilon r, epsilon naught, and epsilon r says 4. And where now this one here is, let me say from the center, this is A prime. How would you think to solve this problem?
So I think you would use like well, you would first find the capacitance of the center part to the first radius, and then you do the same for the second radius, and then you would combine them in series.
Yes, exactly. So the total for this, C total,
It's 6 o'clock.
it would be C for, let me use, I will show it here. It's going to be C for this and plus C for this. So it's C1. And if this little one is C2. So it's going to be series combination of C1. I will show it here. Yeah, C1 in series with C2, which means 1 over C total will be 1 over C1 plus 1 over C2. And how do we find C1? C1 is going to be this formula we had, 2 pi is epsilon is free space L divided by natural logarithm of B. Now the larger dimension is going to be A prime. The smaller dimension is going to be A. and C2 will be 2 pi epsilon r epsilon naught L ln of B over A prime. Okay? You compute these two, and then you find the series combination. Is that clear?
Can you show me where B would be at on the capacitor, on the, the coaxial?
What do you mean B?
Yeah, like the length of B.
The
Can you show
length,
me like, yeah.
it's like, I assume that the external is just does not have any thickness, all right? So it's the inside is from here, to be accurate. I'll show you. It's from here to there, to B. It's from there to there.
Oh, okay.
Okay,
Thank you.
you're welcome. So I don't need this one here. What would you do? Let me now take the same thing as before. Copy. So now we solve another problem. See? Paste. Okay. So now, what I do is remove here this one, and I put material, but I put it like, how do I do it? Yes, I put it like this. Instead of having material everywhere, I have it only in two. I have created that kind of a comb kind of thing. How would you calculate that? What do you think? So it's like 1/4. Each one of them is 1/4, the way I have it.
Wouldn't you just calculate that like two capacitors in parallel, since the position of those quarters don't really matter, and it's basically just one half with a different dielectrics?
Mm-hmm. Yes, that is so accurate. So that is equivalent practically. So let me write it here. So ideally will be 4 capacitors, all right? I could say that the total capacitance here is like the parallel combination of 4 capacitors, but every 2 of them are the same. These 2 are the green ones. They have the green material, and the other 2 is with the air. So practically you calculate, this is C1, C1, and this is C2, C2, and then this is C2, C1, and C1. And it's the parallel combination of the 4. Do you have any questions about that?
So what makes them parallel instead of a series for the coaxial?
The fact that they what makes them parallel is the fact that they share the same 2 conductors.
Oh, okay.
All
Makes
right?
sense.
Yeah.
for this case, since they are, each one is just 1/4, are we going to use the same, equation, the full equation, or we're going to just use half of it?
What you're gonna, so here is where you have to go. And then, let me see if the book has something, or if, so there you have to be careful on how you're gonna use the equation. So in fact, is the following. If the equations, the way we did them, you remember they said that, so let's go now to calculate those, all right? That's what we're gonna do. Let's try to think on how we calculated this one, even without the material. The way you calculate it is if you go back to page 253, you see that you will have to find C. You don't have to go very far. I mean, there are two things you have to do. To find C, you will have to divide from definitions. C equals, let's assume that we're looking at one. C equals Q1 over V. Now, what is common in these two capacitors and what is different? What is common, these capacitors do share the same voltage, but they do not share the same charge, all right? In this case, they do share the same charge, but they do not share the same voltage. That's what happens. With this one, if we assume that, let's assume for a moment that the charge distributes, for simplicity, distributes uniformly, which is not quite the case though. But I will assume that the charge distributes uniformly. In that case, each one of them has only 1/4 of the charge. So practically, each one of them, in terms of charge, if I assume that the charge distributes uniformly, which is a good assumption, I mean, it's not an accurate, but it's a good assumption, then Q1 is going to be Q over 4. And in that case, what is going to happen is you're going to find that your okay, let's assume this one, which is for simplicity. I mean, you want to do it as an assumption. Then in this case, you're going to find, since V is constant, that your C1 is going to be, let me see how they, well, your V then, in this case, let me see, is going to be, okay, so your C1, since it's going to be with the dielectric, is going to be Q over 4. And then it's going to be, but Q from the original, all right? The original Q over 4. And then it's going to be 1 over 4 2 pi. If it has a dielectric, as we'd say, this is epsilon r, epsilon naught. L, they share the same length. ln b over a. That's C1. And C2 now is going to be, it's going to have also, it's not exactly that, it's Q over 4 divided by V. All right, it's Q over 4 divided by V, but it's going to be 1 over 4 2 pi epsilon naught L, since it does not have the dielectric, logarithm of B over A. So this is going to be then C1 and C2, and then the total sum, the C total, will have to be 1 over 4, the sum of the, and then it's going to be 2 pi L, this is common, B over A, and then epsilon naught And then what we are going to have in there, oops, sorry. And then we are going to have 1 plus 1, so 2 plus 2 epsilon r. So it's going to be 1 over 2 epsilon r plus 1. And then you have 2 pi L epsilon naught over ln v over a. So practically it's like the arithmetic average between the two of epsilon of this, the way I did it. So it's like you think that it's blending, like half of it is half of it only has the dielectric, and the field is like sees only the arithmetic average between the two dielectrics in reality. As if half of it was epsilon r, the other half was, one half had epsilon, the other had epsilon naught, and then practically when you sum them up, this is like which is true, that's how it works. So that will be one way to solve it. I mean, that's how I would.
Okay, thank you.
Sure. So
Professor?
yes,
Sorry, were you saying something?
go ahead.
Okay. I see that you just used the equation that you pulled out of the book
Yes.
from a coaxial cable. That
Mhm.
equation that we use. Do we, if we get this equation on the exam, can we just use it as it is, or do we have to derive it from Gauss's law and the?
No, you don't have to derive anything.
Okay.
Use the equations from the book the way they are.
Okay.
As long as you are careful to replace, if there is a notation, say, of something in the book, and you're placed with the appropriate thing. But yeah, no, you don't have to derive things.
Okay, thank you.
You're welcome. Okay, what else are we going to? Do? What kind of problems do you want me to solve for you? Any other questions? So we did some electrostatics, capacitance is parallel plate. You remember, in case I give you something with parallel plate capacitors, with point charges, I have different point charges. And we did that with point charges, with capacitors, the coaxial, the parallel plate, you know how to do this, all right? So when we talked about having a parallel plate and then different materials, how are you gonna do this? Let me see. Let's assume that you have this green here. And then you have this one here. And then you have something else. How would you solve that one?
You first add the two layered ones in series, and then you add the equivalent of that in parallel with the one on the right.
Yes. And when you do, you remember that this can be area A1, A1, and this can be A2, all right? They have different areas because I can feel different. It might not be half and half, when I keep half air and the other half I feel. They share the same age, they share the same conductors, not all of them. I mean, the left and right side, but they have different areas. And they have also different thicknesses, okay? So you know how to do that. H1, H2 here. Yeah, so you find the capacitance, like this is one capacitor, series with this one, and then in parallel with this one, as if they were independent capacitors here. Which is in fact what we've done here, as if the three were independent capacitors. So we use like 1/4 or something, because they have 1/4 of the area practically, if you like. That's what we did. So if I had 3 here, you would use, if I had 3 equal, if I had only half, you would use 1. Remember, if I had like another coaxial that was like like this, then you would use 1/3 here if it was divided, 1/3 here, 1/3 there for the capacitance, all right? It's gonna be like, because they share only 1/3 of this perimetry, both in and out. Same thing like you do here.
So for the parallel plate, this problem, we can use the same formulas that we used for the capacitor
Yes.
for the coaxial cable.
Well, not the same formula. The coaxial has the logarithm, and the parallel plate waveguide is C is epsilon A over H, but A changes, or H changes. Here it has the logarithm, but assuming, if you look at the area is not directly shown, but it's part of, as I said, of the Q of the capacitor. If you go to 250, you will follow my lead, as I said here. What I said here, that they share like the areas that they have, each one of these quarters is like 1/4 of the area of the inner and 1/4 of the area of the outer conductor. That makes it 1/4 of the capacitance of the total. If the total, say, here is how you have to think about it. C2. C2 is the quarter of a capacitor if it were the whole thing to be filled by air. See how I'm calculating C2? C2
Yes.
would be 1/4 of a coaxial, as if the whole thing was filled with air. C1 will be 1/4 of a coaxial, as if the whole thing was filled by epsilon.
Okay.
That's how you get it. So, and in some ways we do the same here, but here we have explicitly the area incorporated. So in the coaxial, you don't see it explicitly as we see it in the parallel plate waveguide. So in the parallel plate waveguide, you do like, you have the area explicitly incorporated. So now you, and then the depth, of course, or the thickness between, or the distance between the two parallel plates explicitly incorporated here. So it's easier to do it like that. In the coaxial, you have to think it in a little bit different way, because you don't explicitly see the perimeter of the inner or of the outer conductor. That's why we think it that way.
Yeah, now I get it.
Yeah.
Thank you.
You're welcome. What other questions you have that I can help there?
Professor,
Yes, go ahead.
I guess I have a follow-up question to the question you just previously asked. So suppose if in that example where you had 1/3 split up with all different dielectric, the one you just erased, it's okay, you don't have to redraw it.
Okay.
But suppose that one of those dielectric thirds was like made up of the same material of like the jacket of a coaxial, where it's hard for electric field to get through that. And suppose like it's essentially zero electric field going through that, because the dielectric constant is so high. Would you then be able to solve that problem only using like 2/3 of the area, or would you still solve it as if all the other dielectrics?
So what you're telling me is the following. Let's take the coaxial, all right? I will only use not 1/3, I will use 2. So let's assume that I have a coaxial like this. And assume that I have half of it with very high density material. That's what you're telling me, isn't it?
Yes.
Okay. So let's see what happens. If I have a very high density material, then the electric field is going to be, so the electric field goes like that. Okay. And the electric field is when it goes through the when you are going, if you have an air dielectric interface, the tangential electric field is continuous. So the electric field is going to be like this everywhere. It's going to be constant. It's not going to change because there is a material. What is going to change is the flux density. So the flux density, if I were to show the flux with green, it will be here like this. It's not going to change in the direction, but it's going to change in magnitude. When it gets inside the material, the dielectric, so it's going to get much stronger because the flux density is the product of the electric constant and E. So D is epsilon E, epsilon not E here, and D equals epsilon E here. And if epsilon is much larger than epsilon naught, then D in this dielectric, D is going to be much larger than D naught. All right? Do you agree with that? So your electric field remains the same, but your flux density becomes a lot stronger inside. Now, what does that really mean for you? It means that most of my, the flux density also, you remember that what we said, that D is directly related. What is not right? Okay, D, okay. Let me see how much I have, 0. Okay, I have, my pen is not writing, but I will let it charge a little bit. I just want to tell you, so inside the pink area, the magnetic flux density is very strong because of epsilon, much, much stronger than the other area, not the electric field, the flux density. But what happens then? The flux density directly correlates with the charge density. You remember that? We said that if you go very close to the surface of a conductor, especially we did it for parallel plate, all right? So we looked at the parallel plate capacitor and we said, right at the surface of the capacitor on the metal, the value of the flux density equals the charge density at that point. What therefore that means is that as you increase your flux density, your charges tend to accumulate where the flux density becomes stronger. So your charges will come and all accumulate inside the area on the surface where it has the high density dielectric, the high epsilon dielectric. So even if your field seems to be the same, your charge density is going to become a lot stronger inside, and therefore the charge is going to distribute not with the same, is not going to be equally distributed around. So you're going to have much more charge activity inside the dielectric. And this is going to increase your capacitance in that area. All right. And because it's in parallel, so your overall capacitance is going to increase. It's not like that the field is going to go zero anywhere. It's just that the flux density is going to increase substantially in the area where you have the very high epsilon dielectric. And therefore your charge is going to go and accumulate there because of that, which is going to increase the capacitance of that side, of the half side is going to increase tremendously. But because the two capacitors are in parallel, it's going to increase the whole capacitance.
Okay, I understand mathematically how that works. I'm still trying to think about how that physically works because in the high density dielectric, there's going to be fewer free electrons for the electric field to act on. So wouldn't that mean there'd be less charges on that side? I mean, that's how I'm thinking about it.
I'll tell you what, if you have a very high, which we have not covered enough of the physics of dielectrics to see why you're going to have more charges there. You're going to have more charges because the dielectric by itself is going to create what is called the polarization charge. So because the dielectric, when it has high density epsilon, creates those dipoles, like there are no more free electrons in a dielectric. There are no electrons that run around. It's not like a conductor. But because of the high D or the high epsilon in there, you have plenty of electrons that will not leave the atom, but they will be displaced in the atom. So the atom, instead of being like a nice round, like a solar system, all right, a nice round core and around a nice electronic cloud, is going, the electrons are going to be displaced away from the positive charge. They're not going to separate. They're going to be like connected but displaced. So you're going to have the center of the negative charge and the center of the positive charge displaced, and that is called a dipole. And because of the of the magnetic flux lines, they will try to align along those lines, and therefore it creates more charge in there, not less, but not because of free electrons. So you have more charges inside the dielectric. And that's why your capacitance is higher, not because of more free electrons, but because of more polarization charges.
Okay, that made a lot of sense. Thank you.
You're welcome. Any other question? I think, we covered so much. You're not going to see anything different from anything that I've shown you so far. In fact, I even ran out of ideas. What else to give you, to tell you the truth? So if you look at all of this that I covered, and I will take now the notes, and I will process a little bit. I'm not going to do too much to the videos because I have to remove people who speak and their names show. That's why I have to. Otherwise, cannot put them on YouTube. And yes.
I had a question. It's for the exam. Do you know how many questions is going to be in the exam?
One problem with maybe 2 questions, but one is going to lead to the other. They're not going to be 2 separate. I will use one question to lead you to the second.
So only 2 questions on the exam?
Yes.
Okay, thank you.
Yep, you're welcome. But you're going to get credit for all partial work, all right? It's not like that I'm gonna grade the exams. I usually do that. I grade all of the exams.
Okay, just because I'm asking this question because I have other exams at the same time. So should I go beyond and going all over all the lectures and stuff like that, or do you think this practice problems are good to the topics in them to prepare us for the exam?
Listen, so it's up to you to make a judgment. I don't know how comfortable you feel. Of course, I'm not going to give you one of these problems. There's going to be a small variation. It's going to be variation from these problems. Now, how you are doing very well in this class. How comfortable you feel managing this variation is up to you, all right? So I cannot tell you, do this. I'm not gonna tell you, don't study the other things. And then you come and tell me, you told me not to study the other things, but I needed to know that to take care of this. And I don't know. I will tell you, pay attention. Instead of giving you that directive, I will do something different. I will say, pay attention to the problem we solved, because I'm going to give you one of these with a variation. It's not going to be identical, obviously, because otherwise you can take the solution and copy it, all right? I will put a variation.
Yeah, I was speaking like topics wise. These kind of like the concept that we need to
For the
understand.
topics we covered, yeah, of course, in terms of topics wise, yes, focus on these types of topics, if that's what you asked. Yes,
All right, thank you.
you're welcome.
Professor, I have a quick question also about the exam. You may have already talked about it, but after our exam closes out, like, do we have a window to scan our work and upload it?
So you're gonna I'm gonna leave it open. So I think, how long does it take you for you to scan it and then upload it?
Only a few minutes, like
10
depends
minutes,
on,
because I
yeah,
will
no
keep it
more
up
than 10.
for an hour.
It's like 10 to 15 minutes to
Oh, yeah.
upload it.
It really depends
And the
on
class is what, 50
like-
minutes, isn't it?
Mm-hmm.
Yeah.
Yes, ma'am.
I will keep it up for an hour and 5 minutes.
Okay, sounds good. Thank you.
You're welcome. Because I know some students have to leave already on the hour because they have other things. But I will leave it up for an hour and 5 minutes. Okay, well, I think, let me know if there is anything else from me. I just need to go and try to upload everything from today before tonight. So everything is available, and the solutions for the team homework. Okay? I'm sure you'll do well. Take care.